Hey guys, alright, so let's continue with section 4.1. The title is called Polynomial Functions and Models. So the first video of 4.1, we completed the first 2 pages of notes. Okay, so this one, and we ended here where you are supposed to fill this out on your own. So now where we're going to continue or pick up is this page right here. Okay, so this page. So before we start, why don't you go grab your calculator? Because this is the part where you're going to have to do on your own. On the same screen of your graphing calculator, I would like for you to graph both. Okay, let me zoom in. Y sub 1 equals x squared. Okay, sketch that out right here. Make sure you use your table so that way you have nice 3 points for y sub 1. Y sub 2 equals x to the 10th. Sketch that out neatly. Label which one's y sub 1 and which one's y sub 2. Okay, so make sure you have this done over here. Similarly, over here, I would like for you to either use a graphing calculator or by hand. I prefer a graphing calculator and really zoom in at the near the origin. Okay, so when you graph this out, I only want you to have, how about this? Label every 3 tick marks as 1 unit. So that way it's totally consistent. Okay, so why don't we do this? So this is 1, this is 2, this is -1, this is -2. What I really want you to focus on is near the origin and then see what it looks like. Same thing over here. 1, this is 2, this is -1, this is -2, +1, +2, 1, 2, 3, and 1, 2, 3. Okay, so -2. So keep the labeling just like this, but you're going to have to do it on your calculator on your own and sketch both units out, or both sets out. And make sure you label which one is y sub 1 and which one's y sub 2. Okay? That way I want you to really see, hey, what's going on near the origin. Okay? Even though they look similar, the only difference is near the origin. So hit pause, hit pause, hit pause, and go and do that before you continue. Now that you have completed those 2 sets of graphs, let's define some more vocabulary. Real zero, if f is a function and r is a real number for when f of r equals 0. Okay? Let me see. Okay. If f is any function, in this case we just call it a function, and r is a real number for when I put r in as an input, okay, so for when f of r equals 0, then r is called real 0 of f. Okay, and the reason it's called real 0 is because the output is 0. So on your calculator, you're going to see that, hey, when you hit second trace, you're going to see 0, intercept, you know, maximum, minimum. So real 0 is when I want to find where the x-intercepts are. So some also known as, aka, okay, aka for real 0. The first one, if you remember, it's also called r is an x-intercept. Okay. Because at x-intercept, y is 0. Another one that's also known as is r is a solution of f of x when it's set equal to 0. Okay. And another one that real 0, it also can be called, is r of x minus r is a factor of f. Okay, so all of these 3 different things here, it's really talking about this one thing, the real 0. So all 4 of these is talking about the same exact location if we were to graph it out. Okay. The next one. zero multiplicity. So the word zero is talking about the solution, right? So multiplicity is how many times we have it. So the definition is zero multiplicity is when the factor x minus r occurs more than once. Okay. If x minus r to the power of m is a factor, then r is a 0, which makes sense because that's what we said, right? If it's a factor, then it's also called a 0. But it has multiplicity. Multiplicity m times. Okay? That means it's repeating as many times as it wants to be. So for example, i.e., f of x equals x minus 2 squared. Okay? So we've seen this before. Okay? This is a quadratic or a parabolic shape. But look at this. At the x-intercept, it's at positive 2, and it has a multiplicity of 2. Well, what does that really mean when I have it? Well, let's quickly sketch it out, right? We know that we have an x-intercept at 1, 2, positive 2. Okay. Let's plot another point when x is 0. 0 minus 2 is negative 2. Negative 2 squared is 4. So 1, 2, 3, 4. So there you go. That means on the other side, I should have another one. So this is my sketch of my parabola. Well, look at that. Because it's a multiplicity of 2, notice how I'm only going to intersect this at one place. And in a little bit, we're going to see, hey, what does an even multiplicity do? And that's this right here is going to touch this or is related to this, okay? Even multiplicity. And we're going to answer that. Sine of f of x does not change from one side of R to the other side of R. Okay. The graph touches, and this is huge. Okay, the graph touches x-axis at R. Okay, so now let's use this piece. Okay, so just like what we had here. So when we have x minus 2, let's sketch this over here. Let me just get a thinner pencil. Okay, so here's 2, and we said when x is 0, it's 2, 4. And then that means it's symmetrical over here, so we have this awesome looking parabola. Okay. All right. There you go. Okay. So look at this. So according to this, the sine of f of x, okay, over here on the left, so here is our axis of symmetry. On the left side, the sine is positive. Y, f of x is positive. Y is positive. And on the right, okay, it's also positive. Okay, so this is R. R is this piece. Oops. X equals to R, and R happened to be, for our example, R equals to 2. R equals to 2. Okay, so when this is my R value at 2. So the sign on the left and the sign on the right, they don't change. They are both positive, and they can be both negative as well. It just doesn't change. The most important piece is that the graph touches the x-axis at all even multiplicity. Okay, so that's something that you want to keep in mind. Okay, now we are going to flip over. Okay, so because we did even multiplicity, of course we are going to do odd multiplicity. Odd multiplicity, we're going to do an example as well. Okay, and then let's see what happens when I have an odd multiplicity. Odd multiplicity, the sign of f of x changes from one side of R to the other side of R. Okay. The graph crosses, okay, super important, x-axis at R. Okay. So let's graph this out, i.e. f of x equals x minus 3 to the third power. So R is 3, multiplicity of 3. Okay, so look at this one. So real 0, R equals 3 with the multiplicity of 3, okay? Multiplicity of 3. So let's graph it out. We know anything that has a third power, it looks like a lazy S. But in this case, I have it going to the right. If you look at this transformation, it's to the right by 3. So it's going to go 1, 2, 3. Okay. When x is negative, when x is 2, how about that? 2 minus 3 is negative 1. Negative 1 to the third is still negative 1. Okay. Let's go to 4. When x is 4, 4 minus 3 is going to be 1. 1 to the third is 1. How about when x is 1? 1 minus 3 is negative 2. Negative 2 to the third is going to be negative 8. So 2, 4, 6, 8. So that's okay. And let's do 5. 5 minus 3 is going to be positive 2. Positive 2 to the third is going to be 8. So 1, 2, 3, 4, 5, 8. Okay. So this is what I have. So there is our f of x. Now it says here the sign of f changes from one side of R to another. Okay, keep in mind this is my R value right here. See that right there? R is at 3. This is negative f of x and this is positive f of x. So notice how from one side to the other the sign changes. And because the sign did change, it crosses over the x-axis. So anytime and every time you have an odd multiplicity, and it doesn't matter what function you have, it will always cross over the x-axis. Okay. All right, turning points. Turning points are points where the graph changes from increase to decrease, or vice versa. Okay, so let's just make up some random graph. All right, let's see. Let's rescale this. Okay, so let's do a point here and go like that for me. So this is negative 3, 0. And ooh, how about that? And shoot up. Just really random. So let's see, this is negative 1, this is positive 1, positive 2. Let's make this at 3, okay? So this is 3, 0. Just make it easier. And I'm going to keep the y the same. So 1, 2, 3, 4, 5, 6, 7, 8. Let's make it 0, negative 8. All right, so this is just a random graph that I made up. All right, so now that we have, I changed the x scaling, but keep the y scaling the same. Okay, so turning points. I have 2 turning points, okay? So i.e., in this example, I have 2 turning points. And turning points are kind of like the minimum maximum, okay? So here's a maximum, that's one turning point. Here's a minimum, that's another turning point. So it's kind of like that. So where the graph changes from increasing to decreasing. Let's see if that's true or not. Here I am, increase, 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 and then all of a sudden I gotta go whoop. Okay, so now I got to go decreasing. So I went from increase to decrease. So this is a turning point right here. And then decrease, 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 and then went whoop, went straight up. So that's a decrease to increase. So these right here are my 2 turning points. Okay. And some properties. Here we go. If f has a degree of something called n, okay, then this f function has at most n minus 1 turning points. Okay, So this function right here, guys, is a degree of 3. Okay? Degree 3. And it has at most 2 turning points. So that's what we have. Another word. If f has n minus 1 turning points, then f has at least n degree. Okay, so what that means is, hey, if I have 2 turning points, it doesn't mean that I have a degree of 3. I could have 3 or 4 or 5 or 6 or 7. So at least mean the minimum is 3. Okay. End behavior, it's something that we've seen before, and let me look back for you. End behavior, it's also called, okay, end behavior is also called the Powell function of n degree. Excuse me. So it's very similar, okay? So end behavior, it's a function. Okay, so is a function. So make sure we have a y equals or an f of x equals. And, okay, it's a function. For large values of x, either positive or negative. Okay, so it can be negative, it can be positive. Okay, the graph of the polynomial, and let me remind you of the polynomial function that we defined on the very first page. Remember this awesome looking function? F of x equals a sub n times x to the n plus a sub n minus 1 times x to the power of n minus 1 plus dot 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 a sub 1 times x plus a sub 0. Remember this definition of a polynomial? Okay. This graph resembles y equals a sub n times x to the n for large values of x. That's what it means. Okay, so an n behavior, so this is my n behavior right here. Because as x gets really, really, really large, okay, these things don't matter as much. So the only thing that's going to matter is this very first term. So what you want to get out of this is the n behavior is pretty much the first term if you write it in descending order. Okay? So let's move on to example 1. And if I'm going too fast, please do hit pause and catch up. And if you are struggling in class because you don't understand the notes, then please listen to it the first time without writing. I beg of you. And then the second time, listen to it twice. Then the second time, you might want to start writing. Okay? All right, example 1. And this is probably the only one we're going to finish in this video. Example 1 says, determine which function is a polynomial. State the degree if it is a polynomial. Explain why if it isn't or if it's not. So, A, 5x squared plus 4x to the 4th equals f of x. What I'm going to do is I'm going to rewrite this in descending order, and I encourage you to do so with every single function that you see. Okay, that means the highest exponent goes first. So I'm going to rewrite it, f of x equals 4x to the 4th plus 5x squared. It is a polynomial because the exponents are all positive integers. So we're going to say yes. Okay. And it says, hey, if you say it is a polynomial, state the degree. So the degree of this one is, remember, the degree of a polynomial is the highest degree. So the highest degree right here happens to be 4. The degree is 4. Okay. All right, let's do B. F of x equals 3 minus 5 over 2x. Let's again write this in descending order. That means highest exponents first. So f of x equals negative 5 divided by 2 times x plus 3. Okay. All right, so let's look at are exponents. This right here actually has an exponent of 1. This right here doesn't have any x. So if I compare between an exponent of 1 with this x and no x at all, this is a degree of 1. And so therefore, because you do have a degree, okay, the exponent is a positive number, so this is also a polynomial with a degree of 1. Now you might ask, well, Mrs. Tran-Bloom, you have a fraction here. Not only do you have a fraction, you have a negative fraction. Well, remember, the coefficients, okay, these numbers right here, okay, those numbers, those leading coefficients, that means these, they can be anything they want to be as long as they are real numbers. It doesn't matter. It does not affect or change the definition of a polynomial. Only changes is the degree. Okay, let's work on this one. These two are so similar. Can you guys see that right there? This is a fraction. There's a constant. There's a constant. So let's write it in order. Okay, so I see an x. I might want to put it first. So it's going to be negative 5 over x plus 2. So far, looks good. Except this right here currently, the x is not on the side. The x is in the denominator. So you're going to rewrite it again. F of x equals. If I want to make x on the side, I would have to bring it up. Okay? Like that. Currently, it has a positive 1 degree on the bottom. To bring it up, you make it a degree of negative 1. And then bring the 2 over. So currently, this has 0 degree. It has a degree of negative 1. So therefore, this is not a polynomial because according to our definition of a polynomial, all of your exponents must be positive integers. So this is a no because f of x has a negative power or degree, whatever you want to use, okay? Okay, so now we are on our very last one. F of x equals square root times square root of x minus 1. You can leave it the way it is, or you can distribute this out. So f of x equals square root of x times another square root of x. The square root will cancel. I'm going to end up with positive x. Square root of x minus 1 is going to be minus square root of x. Okay? Okay, so well, that looks really good. That has an exponent of power 1. Okay? Well, if you want to rewrite this, f of x equals, this is going to stay as a power of 1. A square root is the same thing as a power of a half. Okay. So again, according to our definition of a polynomial, all the exponents, okay, n's, must be positive integers. Well, a power of half is definitely not an integer. So we're going to say this is no again, and the reason is because f of x has a non-integer power. Okay. Integer means whole number. Remember that? So because it has a fraction, it would not be a polynomial. All right. So with that said, we have done example 1, all of example 1. What I would love for you to do right now is go ahead and complete check for understanding A and B on your own. Okay. Don't forget to give me the reason of why if it's not a polynomial. If it's a polynomial, make sure you give me the degree. Okay, so I'm going to write on your own, both. Okay, this is the end of our video. Please complete these right away so that way you can get a completion stamp the next time I see you. If you don't do it now, you might forget. So just hit pause and just do it. Have a wonderful day, and I will see you guys in class.